Right now, over the South Atlantic Ocean, Earth's invisible magnetic shield, the one protecting every living thing from harmful solar radiation, has developed a massive weak spot. And according to 11 years of continuous satellite measurements, just confirmed this past September, that weak spot is growing faster than scientists predicted. It's already expanded by an area half the size of Europe. Satellites passing through experience radiation spikes. The International Space Station powers down systems every time it crosses overhead. And now, researchers tracking this anomaly have discovered something nobody expected. It's splitting into two distinct zones of weakness, spreading across thousands of miles of ocean between South America and Africa. This is happening on a scale that defies previous magnetic field models. Stay with me for the next several minutes. In this video, we're going to explore what this growing weakness means for our technology, our planet, and potentially our future. We'll dive into why this invisible shield exists in the first place, what's causing it to weaken in this specific region, and what the splitting pattern tells us about what might come next. Most importantly, we'll look at what scientists are discovering in real time as they track this phenomenon from space. If understanding what's really happening above our heads and beneath our feet matters to you, hit that like button right now. Subscribe to this channel so you don't miss updates as this story develops, because it is developing. And drop a comment telling me where you're watching from, because this magnetic shield covers every single one of us, no matter where we are on Earth. I want to know if you're watching from the Americas, from Europe, from Asia, from Africa, because understanding your connection to this invisible protection changes how you see this entire phenomenon. Let me paint you a picture of what we're dealing with. Imagine an invisible force field extending tens of thousands of miles into space, constantly deflecting charged particles from the sun that would otherwise erode our atmosphere and increase surface radiation. This isn't science. This is the Magnetosphere, Earth's natural defense system generated by the churning liquid iron core beneath our feet. For most of human history, we had no idea it existed. We couldn't see it. We couldn't feel it. We lived under its protection without knowing we needed protection at all. But in the satellite age, we became aware, and more than aware, we became dependent. Every GPS signal you've ever used, every weather satellite image, every communication link that makes modern life possible exists because this magnetic shield protects the electronics we've placed in orbit from space radiation. And that shield has a wound, a vast, growing region where the protection drops to half its normal strength. Scientists call it the South Atlantic Anomaly, and it's been known for decades. Satellites passing through this region experience what engineers call bit flips, radiation particles striking computer chips and flipping binary ones to zeros, causing errors, malfunctions, sometimes complete system failures. The Hubble Space Telescope, one of humanity's most sophisticated instruments, automatically shuts down its observations every time it passes through this zone. The International Space Station, when crossing this region, requires astronauts to avoid certain modules where radiation exposure climbs significantly higher than in other parts of their orbit. These aren't theoretical concerns. These are operational protocols developed because the weakness is real and measurable. But here's what changed. Here's why this story moved from something scientists quietly monitored to something that demands broader attention. The anomaly isn't just persisting, it's evolving. Between 2014 and 2025, the European Space Agency's SWARM mission has continuously measured Earth's magnetic field with unprecedented precision. 3 satellites flying in formation, mapping every subtle variation in field strength as they orbit. And what those satellites revealed in data published just this past September is that the South Atlantic anomaly has split, not expanded uniformly, but divided into 2 separate lobes of weakness. One centered closer to South America, the other shifted towards southwestern Africa. 2 distinct regions where the magnetic field has weakened beyond the already weakened baseline that defined this anomaly for decades. Think about what that means for a moment. We're watching Earth's primary radiation defense system develop a complex structural change in real time. This isn't a gradual, predictable weakening that matches computer models. This is the kind of behavior that makes scientists lean forward in their chairs that generates urgent funding proposals, that shifts this from routine monitoring to active investigation. The pattern of splitting suggests dynamics in Earth's core that we don't fully understand yet. It suggests that whatever causes this anomaly isn't a simple, stable feature. It's an active, evolving process connected to movements happening nearly 2,000 miles beneath the surface. The area affected now stretches across an ocean. If you flew from Sao Paulo, Brazil, to Cape Town, South Africa, you'd spend the entire flight under weakened magnetic protection. That's thousands of miles. And satellites don't have the luxury of avoiding it. Orbits are fixed by physics and purpose. If your satellite's trajectory crosses the South Atlantic, you're passing through this zone multiple times per day, every day, for the entire operational lifetime of your spacecraft, which means every satellite in certain orbital configurations, and there are thousands of them, is experiencing increased radiation exposure every single day. Some handle it better than others, some have shielding, some have radiation-hardened components, but all of them are aging faster in this region than they would anywhere else in their orbit. Let me be clear about something before we go deeper. This isn't an immediate threat to life on Earth's surface. The magnetic field, even in its weakened state over the South Atlantic, still provides substantial protection. We're not talking about radiation levels that would harm someone standing on a beach in Rio de Janeiro or flying on a commercial aircraft. Earth's atmosphere provides its own shielding, and the magnetosphere, even weakened, still deflects the vast majority of dangerous particles. But we're also talking about a system that we depend on in ways that would have been unimaginable 50 years ago. Our technological civilization has extended itself into space. We have infrastructure in orbit, infrastructure that costs billions, that enables trillions in economic activity, that makes everything from weather forecasting to global communications to navigation possible. And that infrastructure is vulnerable in ways that natural life on the surface isn't. What scientists are trying to understand now is trajectory, not just where the anomaly is, but where it's going. Is this splitting temporary or permanent? Will the two lobes continue separating? Will they grow larger? Will the magnetic field weaken further in these regions? Or will it stabilize? And perhaps most significantly, is this related to a longer-term phenomenon that has captured scientific and public imagination for decades? The possibility of a magnetic pole reversal. Earth's magnetic poles have flipped hundreds of times over geological history. North becomes south, south becomes north. It's a natural process, but it's also a disruptive one, and there's evidence that we might be in the early stages of such a reversal, with Earth's overall magnetic field strength declining about 5% per century. The South Atlantic anomaly could be a symptom of that larger transformation, or it could be an independent feature. Right now we're watching and measuring, trying to distinguish between a localized magnetic quirk and a planetary transformation. What I want you to understand as we move forward is that this isn't a story about fear, it's a story about awareness. For most of human existence, we lived without knowing about the magnetosphere. We didn't need to know, but now we do need to know, because now we've built a world that extends beyond the atmosphere. We've created dependencies on systems that operate in an environment where the magnetosphere is the primary defense. And when that defense develops a weak spot that's growing and changing in unexpected ways, understanding what's happening isn't optional anymore. It's essential, not because we need to panic, but because we need to prepare, to adapt, to engineer solutions for a reality we're only beginning to fully comprehend. So let's start at the beginning. Let's talk about the shield itself, the one you've lived under your entire life without thinking about it once. You've never seen Earth's magnetic field, but you've depended on it every day of your life. Every time you've checked your phone's GPS to find your way somewhere, you've relied on satellites that survive in orbit only because this invisible shield protects them. Every time you've checked the weather forecast, you've benefited from instruments in space that would be damaged by solar radiation without magnetic protection. Every time you've made a phone call that routes through a satellite, every time you've used the internet infrastructure that depends on precise timing signals from space, you've been the beneficiary of a planetary defense system you probably never thought about. let me explain what the magnetosphere actually is, because understanding its normal function makes the South Atlantic anomaly's significance much clearer. Deep beneath your feet, about 2,000 miles down, Earth's interior separates into layers. The solid inner core, a sphere of iron about the size of the moon, sits at temperatures comparable to the sun's surface. Surrounding that is the outer core, a shell of liquid iron and nickel about 1,500 miles thick, and that liquid outer core is constantly in motion. It flows, it churns, it convects, driven by heat escaping from the even deeper inner core, and by the cooling effect of the mantle above. These aren't gentle movements. The outer core flows at speeds of several miles per year, which might not sound impressive until you remember we're talking about liquid metal moving in volumes that dwarf all the water in Earth's oceans combined. And here's the remarkable part. When electrically conductive liquid metal moves through an existing magnetic field, it generates electric currents. Those electric currents create their own magnetic fields. Under the right conditions, the conditions that happen to exist in Earth's core, those generated magnetic fields reinforce the original field, which strengthens the currents, which strengthens the fields. In a self-sustaining process that scientists call a geodynamo, it's the same basic principle that powers the generators in every power plant on Earth, just operating on a planetary scale with liquid iron instead of copper wire. The result is a magnetic field that originates deep in the core and extends tens of thousands of miles into space, creating a protective bubble around our entire planet. That bubble, the magnetosphere, isn't spherical. The solar wind, a constant stream of charged particles flowing outward from the sun at speeds of several hundred miles per second, compresses the magnetosphere on the side facing the sun and stretches it into a long tail on the night side. The result looks like a comet made of magnetic field lines, compressed to about 6 to 10 times Earth's radius on the sunward side, stretched to hundreds of Earth radii on the opposite side. And throughout that entire structure, the magnetic field is deflecting charged particles, protons and electrons from the solar wind spiral along magnetic field lines, most of them never reaching the atmosphere. Some particles get trapped in radiation belts, the Van Allen belts, where they bounce back and forth between the magnetic poles. Some eventually precipitate into the upper atmosphere near the poles, where they create the auroras, those beautiful light shows that occur when charged particles collide with atmospheric gases. But the vast majority of solar radiation that would otherwise strike Earth's atmosphere directly gets deflected away entirely, sent around the planet, sent past us. This deflection has been happening for billions of years, long before life emerged, long before anything on this planet was capable of noticing or caring. But it matters profoundly for biological reasons. Without the magnetosphere, solar wind would gradually erode Earth's atmosphere. Mars lost most of its atmosphere this way after its magnetic field shut down billions of years ago. Venus, without a strong magnetic field, has an atmosphere constantly being eroded by solar wind. Earth, protected by its magnetic bubble, has maintained an atmosphere for billions of years, creating the stable conditions that allowed life to evolve from single-celled organisms to the complexity we see today. You've lived your entire life inside this protection without noticing it, because you're not supposed to notice it. At the surface, you don't directly experience the solar wind or the charged particles being deflected. The atmosphere provides its own protection from radiation. It's thick enough that most harmful radiation gets absorbed before reaching ground level. But the technology we've put in space doesn't have that luxury. Satellites orbit above the atmosphere, in the direct path of solar radiation. Without the magnetosphere, every satellite we've ever launched would have a dramatically shortened lifespan. Solar particle events, times when the sun ejects especially intense bursts of radiation, would damage unprotected electronics within hours or days. The magnetosphere makes space accessible for human technology. It turns what would be a hostile, high-radiation environment into something we can engineer for, something we can survive in with proper design. And here's what's fascinating and frustrating in equal measure. We didn't know the magnetosphere existed until the mid-20th century. Scientists suspected something was deflecting solar particles because of aurora patterns and because compass needles pointed north, clearly responding to some magnetic field. But the full structure, the full extent, the actual behaviour of Earth's magnetic field in space, that remained unknown until we started launching satellites and sending instruments beyond the atmosphere. The first scientific confirmation of the magnetosphere's structure came in the late 1950s and early 1960s, when satellites carrying magnetometers began mapping the field. Suddenly, something that had been protecting Earth for billions of years became visible to human understanding. That understanding came with immediate practical relevance, because we were simultaneously launching satellites for communication, navigation, and observation. We needed to know what environment those satellites would face. We needed to understand radiation exposure, charged particle flows, the structure of magnetic field lines and how they guided particles. The early satellite failures, electronics malfunctioning unexpectedly, systems degrading faster than expected, taught us important lessons about the space environment. And those lessons drove the development of radiation-hardened components, shielding strategies, orbital planning that avoids the most dangerous radiation zones. We learned to work within the protection the magnetosphere provides, but that protection isn't uniform. And this is where the South Atlantic anomaly enters the story, not as a recent discovery, but as something that has probably existed in various forms for centuries or millennia. We just didn't notice until we put satellites in orbit and started tracking their failures. The realization that Earth's magnetic field has a weak spot came from satellite engineers noticing that certain spacecraft experienced more malfunctions when passing over a particular region of Earth. Not random malfunctions spread evenly across the orbit, but concentrated failures occurring above the South Atlantic Ocean. When scientists mapped magnetic field strength from orbit, they found what engineers were experiencing, a region where the field dropped significantly below the strength measured everywhere else at the same altitude. A hole in the shield, not a complete absence of magnetic protection, but a thinning, a place where the umbrella has worn thin and more rain gets through. For decades, this was primarily an engineering concern. Satellite designers learned to account for increased radiation exposure over the South Atlantic. Mission planners scheduled sensitive observations to avoid this region when possible. The International Space Station developed protocols to minimize astronaut exposure during passes through the anomaly. It was a known issue, a managed risk, something tracked and worked around. But then the swarm satellites began their detailed continuous monitoring, and the data they've collected over 11 years has transformed our understanding from there's a weak spot to there's a weak spot that's changing in ways we didn't predict. That transformation from stable feature to active phenomenon is why this matters now in ways it didn't matter before. Before we dive into what makes the South Atlantic anomaly special, before we explore the splitting pattern and what it means, you need to understand that you're looking at a dynamic system. Earth's magnetic field isn't a fixed thing frozen in place. It's generated by flowing liquid metal, and that flow changes over time. The magnetic poles wander, the field's strength fluctuates. Features appear, evolve, and sometimes disappear over decades or centuries. We're watching one of those features evolve right now, and we're watching it with instruments sophisticated enough to measure the changes in real time. That combination, a changing magnetic feature and the technology to track it precisely, gives us an unprecedented window into how Earth's deep interior connects to the space environment around us. And what we're seeing through that window is raising questions that will shape how we think about our planet's magnetic future. The South Atlantic anomaly isn't a recent surprise that scientists stumbled upon last year or last decade. It's been there, lurking in the magnetic field structure, for as long as we've had the instruments to detect it. The first hints came in the 1950s and 60s, when early satellites started experiencing mysterious malfunctions over a specific region of the planet. Engineers reviewing failure logs noticed a pattern. Spacecraft weren't dying randomly, they were dying disproportionately when passing over the South Atlantic Ocean. At first, it seemed like coincidence, statistical noise, but as more satellites launched and more data accumulated, the pattern became undeniable. Something about that region of space, directly above that region of ocean, was hostile to electronics in a way that other parts of the orbit weren't. The location is specific and surprisingly large. Picture the South Atlantic Ocean stretching from the coast of Brazil westward to the southwestern coast of Africa. Now imagine a region of weakened magnetic field strength floating in the space above that entire expanse of ocean, starting at an altitude of a few hundred miles and extending upward. The anomaly isn't a small pinpoint. It's a vast zone, covering an area that stretches from roughly southern Brazil across to southern Africa, encompassing millions of square miles of ocean and the space directly above it. When satellites in low Earth orbit, the kind of orbits used for Earth observation, for weather monitoring, for many scientific missions, cross this region, they enter a radiation environment significantly more dangerous than anywhere else in their path. Why more dangerous? Because the magnetic field weakness allows charged particles to penetrate closer to Earth's surface. Remember the Van Allen radiation belts I mentioned earlier? Those regions of trapped charged particles that bounce back and forth along magnetic field lines? Those belts normally sit well above the altitude where most satellites orbit. The magnetic field is strong enough at typical satellite altitudes to deflect particles before they reach that low. But in the South Atlantic anomaly, the magnetic field is weaker, much weaker. The field strength drops to roughly 30 to 50% of what's measured at equivalent altitudes elsewhere on the planet. And when the field weakens, it can't push the radiation belts as far away. The result is that the inner Van Allen belt, normally safely above most satellite orbits, dips down over the South Atlantic. Satellites passing through this region suddenly find themselves flying through radiation levels they're not experiencing anywhere else in their orbit. That radiation consists primarily of high-energy protons, particles accelerated by various space weather processes and trapped in Earth's magnetic field. When these protons strike satellite electronics, they cause what engineers call single-event upsets. A high-energy proton smashes into a computer chip, deposits its energy in a tiny volume of silicon, and flips a bit, changes a 1 to a 0 or a 0 to a 1 in the satellite's memory or processing circuitry. Most of the time, these bit flips are caught by error correction software and fixed automatically. The satellite hiccups and recovers, but sometimes the upset hits a critical system at a critical moment. Sometimes accumulated radiation damage degrades components over time, shortening the spacecraft's operational life. Sometimes a particularly unlucky hit causes a permanent failure, and a billion-dollar satellite becomes an expensive piece of orbiting junk. The Hubble Space Telescope, humanity's premier orbital observatory for more than 3 decades, learned to respect the South Atlantic anomaly early in its mission. Hubble's orbit carries it directly through the anomaly multiple times per day, and the telescope's sensitive instruments, designed to detect the faintest light from the most distant galaxies, are extremely vulnerable to radiation interference. A charged particle striking the detector during an observation creates a false signal, a bright spot that looks like a star or cosmic ray, but is actually just noise from a radiation hit. To minimize this interference and protect the instruments, Hubble's computers automatically shut down scientific observations whenever the telescope passes through the South Atlantic anomaly. The spacecraft goes into a protected mode, waiting until it exits the region before resuming work. This has been standard operating procedure for decades. Every astronomer who has ever used Hubble knows that some portion of each orbit is simply unavailable for observations because of this magnetic weak spot. The International Space Station operates under similar constraints, though with human rather than scientific concerns at the forefront. The station's orbit, inclined at about 51 degrees to the equator, carries it through the South Atlantic anomaly regularly. When the station enters this region, astronauts inside experience elevated radiation exposure. Not dangerous levels for short exposures, but significant enough that mission planners minimize time spent in certain modules during anomaly passes. The station's crew sleeping quarters are positioned in areas with additional shielding. Sensitive experiments are scheduled to avoid anomaly passes when possible. Spacewalks, which remove an astronaut from the station's shielding entirely, are never scheduled to occur during a pass through the South Atlantic anomaly. These aren't dramatic emergency-level precautions. They're routine safety protocols developed from decades of experience operating in low Earth orbit, but they're protocols that exist specifically because this region of space is measurably more hazardous than the rest of the station's orbit. What's remarkable when you step back and look at the broader picture is how much infrastructure we've adapted to work around this single magnetic feature. Satellite designers build in extra radiation shielding for spacecraft destined for orbits that cross the anomaly. They use radiation-hardened components, special versions of computer chips designed to tolerate higher radiation exposure without failing. They write software with extensive error checking and recovery protocols to handle the bit flips that will inevitably occur. Mission operations teams develop anomaly crossing procedures, protocols for what systems to power down or put in safe mode during these high radiation passes. Insurance companies factor anomaly exposure into satellite insurance rates. This is a multi-billion-dollar adaptation to a magnetic field weakness that most people outside aerospace engineering have never heard of. But adaptation only works when the thing you're adapting to remains stable and predictable. If the South Atlantic anomaly stayed the same size, same intensity, same location decade after decade, then the engineering solutions developed over the past 50 years would simply continue working. Satellites would be designed for the known radiation environment, and that would be the end of the story. The anomaly would remain an interesting footnote in Earth science textbooks and a routine consideration in spacecraft design, but not something that demanded urgent ongoing attention. What changed the equation? What transformed this from routine engineering concern to active scientific investigation was the realization that the anomaly isn't stable. It's moving, it's changing shape, and over the past 2 decades, it's been growing. Satellite measurements tracking magnetic field strength over time show that the region of weakness has expanded. The center of the anomaly has drifted westward at a rate of roughly 12 miles per year. The intensity of the weakening has increased, meaning the magnetic field in the weakest parts of the anomaly has gotten even weaker, and the shape has evolved from a roughly circular or oval depression in field strength to something more complex, something that looks less like a simple weak spot and more like a structured feature with its own internal dynamics. That evolution caught scientists' attention because it suggested the anomaly wasn't just a static feature inherited from some past magnetic field configuration. It was, and is, actively connected to processes happening in Earth's core right now. The movements of liquid iron nearly 2,000 miles beneath the surface are continuously reshaping the magnetic field above. And those reshaping processes don't just affect the core or the deep interior, they reach all the way up through the mantle, through the crust, through the atmosphere, and into space, changing the radiation environment that our satellites fly through. We're seeing a direct connection between the deepest parts of our planet and the outermost edges of our technological reach. And that connection is active, dynamic, changing in ways that our models are still struggling to fully predict. The European Space Agency recognised the importance of detailed continuous monitoring when they designed and launched the Swarm mission in 2013. 3 identical satellites, flying in formation, each carrying high-precision magnetometers capable of measuring tiny variations in Earth's magnetic field strength and direction. Unlike previous magnetic field missions that provided snapshots or short-term measurements, Swarm was designed for long-term monitoring. The satellites would map the entire magnetic field every few months, building up a decade-long dataset showing how the field changes over time. Scientists proposed Swarm specifically to answer questions about magnetic field evolution, about how quickly features like the South Atlantic anomaly change, about what drives those changes, about whether we can predict future evolution based on current trends. And Swarm delivered. Over 11 years of operations, from 2014 through 2025, those 3 satellites mapped Earth's magnetic field in unprecedented detail. They tracked the gradual westward drift of the anomaly. They measured the progressive weakening in certain regions. They captured the subtle variations that distinguish different parts of the anomaly from each other. And in doing so, they revealed something that earlier, shorter missions had hinted at but couldn't definitively confirm. the South Atlantic anomaly was splitting, not expanding uniformly in all directions like a growing circle, but dividing into distinct regions of weakness. Two lobes, each with its own centre of minimum field strength, separated by a region where the field was slightly less weak. The anomaly was developing internal structure, and that structure was becoming more pronounced over time. That splitting pattern is what scientists confirmed and published this past September. And that pattern is what demands we move beyond simply cataloguing the anomaly's existence and start asking deeper questions about what causes it, what drives its evolution, and where it might go next. Because a feature that splits, that develops complex internal structure, that changes in ways not fully captured by previous models, that's a feature controlled by processes we don't yet fully understand. And those processes originate in a place humans have never been and can never directly observe, the boundary between Earth's molten iron core and the solid rock mantle above it. To understand why the South Atlantic anomaly exists at all, you need to understand that Earth's magnetic field isn't a simple bar magnet buried at the centre of the planet. It's generated by a dynamic system, a planet-sized engine of flowing liquid metal operating under conditions of extreme temperature and pressure. And like any complex dynamic system, it has quirks, it has irregularities, it has features that arise from the specific geometry and flow patterns of the fluids generating it. The South Atlantic anomaly is one of those features, and its existence traces back to peculiarities in how Earth's core generates magnetic fields and how those fields interact with structures deep beneath the surface. Let's start with the basic geometry. If Earth's magnetic field were perfectly symmetrical, the magnetic poles would align with the geographic poles, the axis of rotation. The field would be strongest at the poles, weakest at the equator, with a smooth gradient in between. Every point at the same distance from the centre of Earth would experience the same magnetic field strength. But that's not what we observe. Instead, Earth's magnetic axis is tilted roughly 11 degrees relative to the rotation axis. The magnetic poles don't coincide with the geographic poles. They wander over time, shifting position by miles per year. And the field strength varies significantly from place to place, even at the same altitude. These asymmetries tell us immediately that whatever generates the magnetic field isn't a simple uniform process. It's complex, it's three-dimensional, it has structure. That structure originates in the outer core, where liquid iron flows in complicated patterns driven by convection, rotation, and the cooling of the planet. Imagine trying to predict the exact flow pattern of water in a pot on a stove. Now make that pot spherical, fill it with liquid metal instead of water, spin the whole thing once per day, and heat it from below while cooling it from above. That's Earth's core, and the flow patterns are correspondingly complex. Scientists describe these patterns using terms like convective plumes and helical flows, spiraling currents of liquid iron rising from the inner core boundary, spreading horizontally, and sinking back down. These flows generate magnetic fields through the dynamo process, but they don't generate a uniform field. They generate a field with spatial variations, with stronger regions and weaker regions, with patterns that reflect the underlying flow structure. Now add another complication. The mantle, the thick layer of solid rock between the core and the crust, isn't uniform either. It has variations in density, in composition, in temperature. And some of those variations are dramatic. Seismic imaging, the same technology used to study earthquakes, allows scientists to create three-dimensional maps of the mantle's interior by tracking how seismic waves travel through rock. Waves travel faster through cooler, denser rock and slower through hotter, less dense rock. By analysing thousands of earthquakes and millions of seismic wave paths, scientists have built detailed pictures of the mantle's structure. And those pictures reveal enormous anomalies, regions where the rock is significantly hotter or cooler, denser or less dense than the surrounding material. The most relevant of these structures for understanding the South Atlantic anomaly is something called the African Large Low Shear Velocity Province, or LESS for short. It's one of two massive structures sitting at the very bottom of the mantle, at the boundary with the outer core. One sits beneath Africa, the other sits beneath the Pacific Ocean. These aren't subtle features. They're enormous, thousands of miles across, hundreds of miles thick, denser than the surrounding mantle rock. Scientists don't fully agree on what these structures are. They might be ancient material left over from Earth's formation. They might be accumulations of subducted ocean crust, material from Earth's surface that sank all the way to the core mantle boundary over hundreds of millions of years. Whatever they are, they're sitting right where the core meets the mantle, right at the interface where Earth's magnetic field is generated. And that location matters profoundly, because these dense structures affect how the core flows. Think of them as boulders in a stream. The liquid iron in the outer core is constantly moving, constantly flowing in convective patterns. When that flow encounters a dense structure sitting on the boundary, it has to flow around it. The pattern changes. The flow speeds up in some places, slows down in others, develops turbulence or secondary circulation patterns. And because the magnetic field generation depends on the flow patterns, changes in flow create changes in the magnetic field structure above. The African Elsveep sits beneath southern and central Africa, about 1,800 miles beneath the surface. Directly above it, at the surface, the magnetic field shows unusual characteristics. And extending westward from that region, over the South Atlantic Ocean, we find the South Atlantic Anomaly. This isn't coincidence. Multiple research studies using computer simulations of core dynamics have shown that when you include the African Elsveep in your model, when you account for how its presence affects core flow, you naturally generate a magnetic field with a weak spot in roughly the location where we observe the South Atlantic Anomaly. The structure deep in the mantle creates a perturbation in the core flow, and that perturbation propagates upward through the generated magnetic field, creating a region of weakness at and above the surface. Here's where it gets even more interesting. The magnetic field lines in the South Atlantic Anomaly region don't just point weakly in the expected direction, north for the northern hemisphere, south for the southern hemisphere. In some parts of the anomaly, the field lines actually reverse. They point the opposite direction from what they should. Magnetic north points south. This local reversal happens because of how the magnetic field is structured deep inside Earth. The main dipole field, the dominant component that makes compass needles point north globally, is weak in this region. But Earth's magnetic field isn't just a dipole. It has more complex components, higher-order multipole terms that are normally small compared to the main dipole, but can become relatively important in regions where the dipole is weak. In the South Atlantic Anomaly, these higher-order components create complex field structures, including local reversals where the field points backward relative to the main global direction. What does this mean in practical terms? It means the anomaly isn't just less protection, it's a region where the magnetic field structure itself is fundamentally different from the rest of the planet. The field configuration that usually shields Earth from radiation is disrupted. Field lines that normally deflect particles away instead allow them to penetrate deeper toward the surface. The radiation belts, normally held at bay by a strong, properly oriented magnetic field, can sink down into lower altitudes because the field isn't strong enough or properly configured to keep them away. Scientists studying this phenomenon use massive computer simulations to model core dynamics and magnetic field generation. These simulations divide the outer core into millions of small cells, calculate the flow of liquid iron between cells, compute the magnetic fields generated by those flows, and then let the whole system evolve forward in time according to the laws of fluid dynamics and magnetism. Running these simulations requires some of the world's most powerful supercomputers, and even then the simulations can only cover thousands of years of evolution, a tiny fraction of Earth's history. But what these simulations show consistently is that structures at the core mantle boundary strongly influence magnetic field characteristics at the surface. When simulations include realistic models of the African Ul, they generate South Atlantic-like anomalies. When they leave that structure out, the anomaly doesn't appear. The connection is clear. But here's the challenge. The outer core is in constant motion. The flows that generate the magnetic field change over time. The African Elsveep isn't moving significantly. It's probably been sitting in roughly the same place for tens or hundreds of millions of years, but the core flow patterns around it evolve continuously. Those evolving flows create evolving magnetic field structures, which means the South Atlantic anomaly, generated by the interaction between core flows and deep mantle structures, should also evolve over time. Its size should change, its intensity should change, its position should drift as the core flow patterns that create it shift and reorganize. And that's exactly what we observe. The anomaly isn't static. It's been drifting westward for decades, following changes in the underlying core flow. It's been growing in area as the flow patterns that create it have intensified or expanded. And now, as revealed by Swarm's 11 years of continuous monitoring, it's splitting, developing a tolobed structure that suggests the core flow pattern creating it has become more complex. We're watching the surface manifestation of deep Earth processes that are impossible to observe directly. The South Atlantic anomaly is a window into Earth's interior, showing us that the core is active, dynamic, constantly churning and reorganizing in ways that ripple upward through the entire planet. Understanding this connection matters for more than just academic curiosity. If the anomaly's behavior is controlled by core dynamics, then predicting its future evolution means understanding how those core dynamics will change. And that's extraordinarily difficult. We can't put instruments in the core to directly measure the flows. We can't run laboratory experiments at core pressure and temperature conditions. We're limited to indirect observation, measuring the magnetic field at the surface and in space, using seismic waves to probe the mantle and outer core structure, running computer simulations to test hypotheses about what flows could produce the observed magnetic fields. It's like trying to understand the engine of a car by only being allowed to watch the wheels turn. You can infer a lot, but you're always working through layers of uncertainty. What scientists are certain about is that the anomaly is real, it's significant, and it's changing. What they're less certain about is precisely how it will continue to change. Will the tolobed structure persist and strengthen, or will it be a temporary phase that reorganizes into a different pattern? Will the overall weakness continue to deepen, or will the magnetic field strengthen again in this region as core flow patterns shift? Will the westward drift continue, or will the anomaly slow, stop, or even reverse direction? These are open questions. They're questions that require continued monitoring, more sophisticated simulations, and better understanding of the core mantle interaction that drives everything. And they're questions with practical implications, because every satellite we launch, every space station we operate, every piece of orbital infrastructure we depend on has to exist in whatever radiation environment the magnetic field creates. If the anomaly continues growing and weakening, the radiation environment worsens. More satellites are affected, more shielding is required, more operational constraints are necessary. If the anomaly splits further or new weak spots develop elsewhere, the safe zones for satellites shrink. Understanding what drives this phenomenon isn't just scientifically interesting, it's practically essential for planning humanity's future in space. But before we dive into those future implications, we need to look at what the Swarm mission revealed about the current state of the anomaly, because the splitting pattern discovered over the past 5 years isn't just interesting data, it's a fundamental change in how the anomaly is structured, and that change tells us something important about what's happening in the core right now. When the European Space Agency launched Swarm in 2013, the mission had clear objectives: map Earth's magnetic field with unprecedented precision, track how that field changes over time, and provide data that could help scientists understand the dynamic processes in Earth's core that generate the field. The mission was designed to operate for at least 4 years, with hopes for extension if the satellites remained healthy. 11 years later, Swarm is still operating, still collecting data, still mapping the magnetic field every few months as the satellites orbit Earth. And that extended lifetime has allowed researchers to observe changes in the magnetic field that shorter missions would have missed, including the structural transformation of the South Atlantic anomaly. The data from Swarm's first few years of operation confirmed what earlier missions had shown: The South Atlantic anomaly existed as a broad region of weakened magnetic field strength stretching across the South Atlantic Ocean. The field strength in the weakest part of the anomaly was significantly lower than anywhere else at the same altitude. The anomaly was drifting westward, consistent with decades of previous observations. These were important confirmations, but they didn't represent fundamentally new discoveries. The anomaly was behaving roughly as expected, based on extrapolating from earlier measurements. But then, as SWARM continued operating through the late 2010s and into the 2020s, something started appearing in the data. The shape of the anomaly was changing in a way that previous measurements hadn't captured in detail. Instead of a single, roughly oval region of weakness, the magnetic field maps started showing a more complex structure. Two distinct regions of minimum field strength were emerging, separated by a zone where the field was weak but not quite as weak as in the two centres. By 2020, this tullid structure was clear in the data, and over the following 5 years, as SWARM continued its mapping, the separation between the lobes became more pronounced. The South Atlantic anomaly wasn't just a weak spot anymore, it was two weak spots, developing their own individual characteristics, while still being part of the same overall anomaly structure. This is what scientists confirmed and published this past September. The paper, drawing on 11 years of continuous SWARM measurements from 2014 through 2025, documented the emergence and strengthening of the tullid structure. The western lobe, centred closer to the coast of South America, showed the deepest magnetic field minimum, the point where the field strength reached its lowest value. The eastern lobe, positioned towards southwestern Africa, was slightly less weak, but covered a larger area. Between them, the magnetic field remained well below normal strength, but didn't reach the extreme lows measured at the centres of each lobe. Think about what this structural change means. When you have a single region of weakness, you can explain it with a relatively straightforward core flow pattern, a single upwelling or downwelling of liquid iron that creates a localized perturbation in the magnetic field. But when that single weakness splits into two distinct lobes, you need a more complex explanation. The core flow pattern creating the anomaly isn't a simple feature. It's a structured pattern with multiple components or multiple centres of activity. The liquid iron nearly 2,000 miles beneath the South Atlantic isn't flowing in a simple circular convection cell. It's developing more complex structures, possibly with multiple upwelling or downwelling regions, possibly with lateral flows connecting different parts of the pattern. Computer simulations of core dynamics can produce these kinds of multi-lobed magnetic field structures. When researchers set up models with realistic core conditions and let them evolve, they sometimes see magnetic field anomalies split, merge, or develop complex internal structure as the underlying flow patterns evolve. So the SWARM observations, while unexpected in their specific timing, fit within the range of behaviours that core dynamo models can produce. What makes them particularly significant is that we're observing this splitting in real time with high precision. We're watching a magnetic field feature reorganize itself on a timescale of years to decades, fast enough for human instruments to capture the process, slow enough that we can track it carefully and measure the changes with confidence. The splitting also has immediate practical implications. A single oval-shaped anomaly has a predictable geographic footprint. Satellite operators know which orbits will cross it, where the crossings occur, and how many times per day a given satellite will pass through the high radiation zone. But when the anomaly splits into two lobes, the geographic footprint becomes more complex. Now there are two centres of maximum radiation exposure instead of one. The safe zones between the lobes might be safer than the lobe centres, but are still more hazardous than regions outside the anomaly entirely. And as the lobes continue evolving, potentially drifting apart, potentially merging back together, potentially spawning additional centres of weakness, satellite operators have to adapt to a more complicated and potentially less predictable radiation environment. The SWARM data also revealed that the magnetic field didn't just split, it weakened further in the lobe centres even as the splitting occurred. The minimum field strength recorded in the western lobe during the most recent SWARM measurements is lower than the minimum strength recorded in the pre-split anomaly years earlier. This means the overall protection in the weakest part of the anomaly has decreased. The radiation belt can penetrate even closer to Earth's surface in these lobe centers. Satellites passing through experience even higher radiation exposure than they did a decade ago. The problem isn't just getting more complex, it's getting more intense. Why is this intensification happening? Scientists working with the swarm data believe it connects to the same core flow changes that caused the splitting. When the core flow pattern reorganizes, it doesn't just change the shape of the magnetic field anomaly, it changes the efficiency of the dynamo process in that region. If the flow pattern becomes less effective at generating a strong magnetic field, the field weakens further. If the flow starts generating field components that oppose the main dipole field rather than reinforcing it, you get localized reversals and additional weakening. The details are complex and require sophisticated analysis of the magnetic field's multipole structure. But the basic picture is clear. Whatever's happening in the core beneath the South Atlantic is reducing the magnetic field strength at the surface above, and that reduction is accelerating in certain locations. Let me be clear about the timescales involved here. When I say the magnetic field is weakening rapidly, or the anomaly is growing fast, I'm speaking in geological terms. The changes Swarm has documented occur over years to decades. This isn't something where you'll wake up one morning and the magnetic field will have disappeared overnight. Earth's magnetic field is generated by processes operating on very large scales. The entire outer core, a region roughly the size of Mars. Those processes have inertia. They change relatively slowly. The liquid iron flows at speeds of miles per year, not miles per second. Changes propagate through the core over decades or centuries, not days or months. But slow in geological terms can still be fast for human infrastructure planning. A satellite might have a design lifetime of 10 to 15 years. If the radiation environment changes significantly over that time span, if the anomaly grows, splits further, or intensifies, then satellites designed for the radiation environment of 10 years ago might not be adequately protected for the radiation environment they'll face toward the end of their operational lives. Launch a satellite in 2020, designed for the anomaly as it existed then, and by 2030 it's operating in a more hazardous environment than it was built for. This mismatch between infrastructure lifetimes and magnetic field evolution timescales is part of what makes the South Atlantic anomaly's changes significant from a practical standpoint. The September publication of the swarm splitting results generated significant attention in the space science and satellite engineering communities precisely because it documented a change that affects ongoing operations and future planning. This wasn't a historical analysis of how the magnetic field behaved millions of years ago. This was documentation of changes happening right now, during the operational lifetime of current satellite constellations. The researchers who published the study emphasized that continued monitoring is essential. The swarm satellites, now operating well beyond their original design lifetime, provide irreplaceable data about magnetic field evolution. Losing that monitoring capability would leave us partially blind to changes that directly affect space infrastructure. And that monitoring is revealing something else that concerns scientists. The overall trend isn't just local to the South Atlantic. Earth's magnetic field strength globally has been declining for at least the past 2 centuries, dropping by roughly 5% per century on average. That's a slow decline, but it's persistent and measurable. The South Atlantic anomaly sits within this context of global weakening. The question scientists are wrestling with is whether the anomaly is just an independent feature, a regional quirk of core flow patterns, or whether it's connected to the broader global weakening. Is the South Atlantic showing us an exaggerated version of what's happening to the entire magnetic field? Is it a symptom of larger changes in core dynamics that could eventually affect magnetic protection worldwide? Some researchers argue the anomaly is indeed connected to global magnetic field evolution. They point to evidence suggesting we might be in the early stages of a magnetic pole reversal, an event where Earth's magnetic north and south poles flip positions. These reversals have happened hundreds of times over Earth's history, occurring roughly every few 100,000 years on average. During a reversal, the magnetic field doesn't disappear completely, but it does weaken significantly, and becomes more complex, with multiple magnetic poles appearing temporarily before the field reorganizes into a new stable configuration with reversed polarity. If we're approaching a reversal, the South Atlantic anomaly could be one of the early signs, a region where the field is already weakening and showing the complex multipole structure characteristic of reversal transitions. Other researchers are more cautious. They point out that magnetic field strength has varied significantly throughout recorded history without leading to reversals. The current weakening trend, while notable, isn't unprecedented. The South Atlantic anomaly could be a temporary feature that will strengthen again if core flow patterns shift. Drawing definitive conclusions about whether we're heading toward a pole reversal requires longer timescales of observation, not just decades but centuries of detailed magnetic field monitoring. And we only have satellite at precision data going back about 50 years. Everything before that comes from less precise measurements, historical records, and paleomagnetic studies that reconstruct past magnetic field behavior from magnetic minerals in rocks and sediments. What everyone agrees on is that we need to keep watching. The Swarm mission has provided unprecedented insight, but its satellites won't last forever. Eventually, atmospheric drag will pull them down, or critical systems will fail, and the mission will end. When that happens, there needs to be follow-on missions ready to continue the monitoring. The magnetic field data isn't just scientifically valuable, it's operationally essential for anyone planning to operate technology in space. And as our dependence on space infrastructure grows, that operational need becomes more critical with each passing year. The splitting of the South Atlantic anomaly, documented over the past 5 years and confirmed this past September, represents more than just an interesting change in magnetic field structure. It represents our growing ability to watch Earth's deep interior processes play out in real time through their effects on the magnetic field. It represents the increasing sophistication of our monitoring systems and our understanding of core dynamics. And it represents a challenge. How do we design infrastructure for a space environment that's actively changing in ways we're still learning to predict? That challenge connects directly to the next question we need to explore. What does all of this mean for life on Earth, for the technology we depend on, and for the future of our civilization in space? Let's address the question that probably emerged in your mind the moment you heard about a massive weak spot in Earth's magnetic shield. Are we in danger? The short answer is no, at least not in any immediate, direct, life-threatening way. The long answer requires understanding what magnetic field protection actually does for us, what happens when that protection weakens, and which aspects of modern civilization are vulnerable versus which are perfectly safe. Start with human biology. You, standing on Earth's surface, are not experiencing dangerous radiation exposure because of the South Atlantic anomaly. The magnetic field, even in its weakened state over the South Atlantic, still provides substantial protection. And more importantly, Earth's atmosphere provides its own shielding. The air above you, miles of nitrogen, oxygen, and other gases, absorbs high-energy particles and radiation very effectively. Cosmic rays that would be lethal in space get stopped by the atmosphere long before reaching ground level. Solar particle events that could kill an unprotected astronaut in orbit barely register as detectable events at the surface. The atmosphere is thick enough that magnetic field variations, unless they're extreme enough to allow particles to penetrate into the upper atmosphere, don't significantly affect radiation exposure for people living normal lives on the ground. Commercial aviation operates at altitudes where atmospheric shielding is thinner than at sea level. Pilots and flight attendants experience slightly higher cosmic ray exposure than ground-based populations because they spend time closer to space. But even at cruising altitude, atmospheric protection remains substantial. Routes that cross the South Atlantic don't carry significantly higher radiation exposure than routes crossing other oceans. The anomaly's effects at airliner cruising altitudes are measurable with sensitive instruments, but they're not at levels that pose health concerns for passengers or crew over normal flight durations. If you've flown from South America to Africa, you flew through the South Atlantic anomaly's geographic footprint without experiencing any harmful effects. The story changes when you leave the atmosphere. Astronauts aboard the International Space Station orbit above the protective blanket of air. They're exposed to space radiation directly, with only the station's modest shielding and the magnetosphere itself providing protection. When the station crosses the South Atlantic anomaly, the radiation environment inside becomes measurably worse. Dosimeters worn by astronauts record higher exposure during anomaly passes. Over the course of months in orbit, those repeated passes add up. A crew member spending 6 months on the station will accumulate more radiation dose than a similar crew member would have accumulated if the anomaly didn't exist. It's not enough to exceed safety limits. NASA and other space agencies carefully monitor crew exposure and ensure it stays within acceptable bounds. But it does mean that the South Atlantic anomaly is a factor in mission planning and crew rotation decisions. Longer missions become more challenging from a radiation exposure perspective when a significant portion of each orbit carries elevated radiation levels. The real vulnerability isn't biological, it's technological. Our civilization has extended itself into space through satellites, and those satellites operate in an environment where magnetic field protection matters enormously. Every satellite in low Earth orbit that crosses the South Atlantic anomaly experiences repeated radiation exposure that degrades components, causes bit flips, and shortens operational lifetime. The economic impact is substantial. A typical Earth observation satellite might cost several $100 million to build and launch. If its operational lifetime is shortened by a few years because of radiation damage accumulated during anomaly crossings, that's several $100 million of value lost. Multiply that across the thousands of satellites in affected orbits, and you're looking at billions of dollars in reduced infrastructure lifetime directly attributable to the anomaly. Some satellite systems are more vulnerable than others. Scientific instruments with sensitive detectors, like imaging systems or particle detectors, suffer performance degradation from radiation damage. Communication satellites that depend on precise signal processing can experience bit flips that cause temporary service interruptions or require sophisticated error correction. Navigation satellites that must maintain extremely accurate timing can see their atomic clock's performance degrade slightly from radiation exposure. In most cases, engineers design these systems with enough redundancy and error correction that occasional radiation hits don't cause critical failures. But occasional becomes frequent in the South Atlantic anomaly, and the cumulative effect matters. GPS accuracy, something billions of people depend on daily, shows subtle degradation when the satellites providing signals are passing through or have recently passed through the anomaly. The degradation isn't enough to make your phone's navigation app fail, but it can affect applications requiring centimetre-level precision, precision agriculture, autonomous vehicles, surveying, scientific research. When a GPS satellite's electronics experience a bit flip from a radiation hit, there's a brief period where that satellite might broadcast slightly corrupted data before error correction catches and fixes the problem. Receivers on the ground using signals from multiple satellites can usually identify and discard the corrupted data, but the process reduces the effective constellation size temporarily. For users in regions where only a limited number of GPS satellites are visible, near mountains, in urban canyons between buildings, at high latitudes, losing even one satellite's data briefly can push positioning accuracy below acceptable thresholds. The South Atlantic anomaly also affects Earth observation data quality. Satellites with optical or infrared cameras pointed at the ground record images with occasional bright spots or streaks caused by radiation particles striking the detector during exposure. Scientists analysing these images have to filter out the radiation noise to get at the real data underneath. For most applications, this filtering works well enough, but for subtle measurements, tracking tiny changes in sea surface temperature, detecting slight variations in vegetation health, monitoring atmospheric composition, the radiation noise can reduce measurement precision or introduce errors. Again, we're not talking about making the measurements impossible, but about making them harder and less certain. Here's what concerns scientists most. These effects are getting worse as the anomaly evolves. The splitting into two lobes means there are now two regions where radiation exposure peaks instead of one. The continued weakening in the lobe centres means the peak radiation levels are climbing higher, and the westward drift means the anomaly is moving into regions where more satellites' orbits naturally carry them, more frequent crossings, more accumulated exposure, more operational impact. If these trends continue, if the anomaly keeps splitting, weakening and growing, then within a decade or two, we might be looking at a significantly degraded radiation environment for large portions of low Earth orbit. Now let me address the question that's probably been building in your mind. What about magnetic pole reversal? The internet is full of alarming articles about Earth's magnetic poles flipping, the magnetic field weakening during the transition, and significant consequences for technology and life. There's truth mixed with exaggeration in these narratives, and it's worth separating them carefully. Earth's magnetic poles do reverse. North becomes south, south becomes north. This has happened hundreds of times over geological history, with reversals occurring roughly every few 100,000 years on average. The last reversal, called the Brun-Hess-Matuyama reversal, happened about 770,000 years ago. So by purely statistical measures, we're arguably overdue for the next one. Is the South Atlantic anomaly a sign that reversal is imminent? Possibly, but not necessarily. During magnetic reversals, the dipole field weakens and the magnetic field structure becomes more complex, with multiple magnetic poles appearing temporarily. The South Atlantic anomaly, with its weakened field and complex multipole structure, does resemble features that models suggest should appear during the early stages of a reversal. The overall weakening of Earth's magnetic field over the past few centuries could also be interpreted as consistent with the beginning of a reversal transition. Some scientists argue we're seeing exactly what you'd expect if a reversal is beginning. But here's the critical context. Reversals are slow. The entire process takes thousands of years from beginning to end. The magnetic field doesn't vanish suddenly. It weakens gradually, develops complex structure, reorganizes, and eventually settles into a new reversed configuration. During the transition, magnetic protection decreases, but doesn't disappear. Life on Earth has survived hundreds of magnetic reversals without mass extinctions. The fossil record shows no correlation between reversal timing and major extinction events. So while a reversal would certainly affect our technology, satellites would face worse radiation environments. We'd need to upgrade shielding and design more radiation-hardened systems. It wouldn't be an overnight catastrophe. It would be a gradual change occurring over timescales that allow human civilization to adapt. And critically, we don't know for certain that we're entering a reversal. Magnetic field strength has varied significantly throughout history without leading to reversals. The current weakening trend could reverse, the field could strengthen again, the South Atlantic anomaly could shrink or disappear. We're working with only a few centuries of moderately precise magnetic field measurements and only a few decades of high-precision satellite data. That's not enough baseline to confidently distinguish between normal variation and beginning of reversal. We need more time, more data, more observation before drawing definitive conclusions. What we can say with confidence is that the South Atlantic anomaly matters now, regardless of whether it's connected to a potential pole reversal. It's affecting technology we use today. It's requiring adaptations in satellite design and mission planning. It's a feature of Earth's magnetic field that we need to monitor and understand, because our civilization's space infrastructure depends on knowing what radiation environment to prepare for. Whether the anomaly grows or shrinks over the coming decades, whether it's a transient feature or the beginning of larger changes, we need accurate, up-to-date information about its evolution to make good decisions about how we operate in space. And that brings us to perhaps the most important question of all. How do we actually monitor something invisible that exists in the impossibly remote depths of Earth's interior and extends thousands of miles into space? What does it take to track a planetary magnetic field accurately enough to catch subtle changes over years and decades? Understanding the monitoring systems gives us confidence that the changes scientists report are real, not artifacts or uncertainties. It also shows us how much effort goes into understanding something as fundamental as Earth's magnetic shield. Measuring Earth's magnetic field seems straightforward at first. Just use a magnetometer, an instrument that detects magnetic field strength and direction, but measuring it well enough to track subtle changes over time, to distinguish real changes from instrumental errors, to map the entire planet's field structure from pole to pole and from surface to space. That's a massive technical and logistical challenge. It requires multiple measurement systems working together, satellites orbiting overhead, observatories distributed across the surface, computer models integrating all the data, and careful analysis to separate signal from noise. The foundation of modern magnetic field monitoring is satellite measurement. Spacecraft orbiting Earth carry magnetometers far more sensitive than anything you can buy in a store. These instruments can measure magnetic field strength to better than 1 part in several 100,000, precise enough to detect tiny variations caused by different rock types beneath the surface, electric currents in the ionosphere, changes in core flow patterns, everything that affects the magnetic field at satellite altitude. But precision alone isn't enough. The instruments also have to be stable over years of operation, maintaining their calibration so that measurements made today can be accurately compared with measurements made 5 or 10 years ago. The Swarm mission exemplifies the sophisticated approach needed for accurate magnetic field monitoring. 3 identical satellites, launched together, flying in carefully designed orbits that allow them to sample different parts of the magnetic field structure. 2 satellites fly side by side at lower altitude, separated by about 100 miles, measuring the magnetic field almost simultaneously from 2 nearby points. This paired measurement lets scientists distinguish between spatial variations in the field, differences between one location and another, and temporal variations, changes occurring over time. The 3rd satellite flies at higher altitude, completing the picture by measuring how the magnetic field changes with distance from Earth's surface. Each Swarm satellite carries multiple instruments. The primary magnetometer measures the field's vector components, not just how strong it is, but which direction it points. This matters because the magnetic field's direction contains information about the field's structure and sources. A second magnetometer provides absolute field strength measurements for calibration. Electric field instruments measure currents flowing through the ionosphere, because those currents generate their own magnetic fields that must be separated from the co-regenerated field scientists are trying to track. GPS receivers provide precise orbit determination, essential for knowing exactly where each measurement was taken, and star trackers, instruments that identify star patterns to determine spacecraft orientation, ensure the magnetometer measurements are properly referenced to a fixed coordinate system. The satellites generate enormous amounts of data. Every few seconds, new measurements come in from all 3 spacecraft. Over the course of a year, Swarm maps Earth's magnetic field hundreds of times, building up a detailed picture of the field structure and tracking how it changes month by month. But raw satellite data isn't the same as understanding. The data includes magnetic signals from many sources, the co-regenerated field scientists want to study, crustal magnetism from magnetic rocks in Earth's outer layers, ionospheric currents, even magnetic signals from ocean currents flowing through Earth's field. All these sources contribute to what the satellites measure, and separating them requires sophisticated analysis. That analysis relies on mathematical techniques that can decompose the measured magnetic field into contributions from different sources. Scientists use spherical harmonic expansions, mathematical functions that describe how fields vary across a spherical surface, to model the core field, the crustal field, and external fields separately. By fitting these models to the satellite measurements, they can estimate how strong each component is and how it's distributed. The process requires measurements from many locations and times to constrain all the model parameters. This is why missions like Swarm need to operate for years. Short-term measurements don't provide enough information to accurately separate the different field components and track changes in the core field reliably. Ground-based magnetic observatories complement the satellite measurements. These are permanent stations, many operating continuously for decades, that monitor the magnetic field at fixed surface locations. There are roughly 200 such observatories distributed around the world, from Antarctica to the Arctic, from remote islands to major research institutions. Each observatory uses carefully calibrated magnetometers in magnetically quiet locations places far from power lines, railway tracks, and other sources of artificial magnetic fields that would contaminate the measurements. The observatories record how the magnetic field changes hour by hour, day by day, year by year at their location. What makes ground observatories valuable despite their limited spatial coverage is their temporal continuity. Satellites come and go, Swarm will eventually stop operating, and there might be gaps before replacement missions launch. But ground observatories keep running, providing unbroken records that can span decades or even a century at some sites. These long records capture the slow drift of the magnetic field, the gradual strengthening or weakening of different field components, the long-term trends that take decades to become clear. When scientists want to know whether the South Atlantic anomaly's westward drift is accelerating or slowing, they compare current satellite measurements against historical ground observatory records to see how drift rates have changed over 50 or 80 years. The combination of satellite and ground measurements feeds into a reference model called the International Geomagnetic Reference Field, or IGRF. This model, updated every 5 years by an international team of scientists, represents the scientific community's best estimate of Earth's magnetic field structure at a particular time. The IGRF provides values for the magnetic field's strength and direction at any location on or above Earth's surface. Engineers designing satellites use the IGRF to estimate radiation exposure for planned orbits. Scientists studying the magnetosphere use it to understand field line geometry. Navigation systems use it for compass corrections. The IGRF is a fundamental reference for anything involving Earth's magnetic field. But the IGRF is a snapshot, not a prediction. It tells you what the field looked like when the model was fit to data, but it doesn't tell you what the field will look like 5 years from now. Making predictions requires understanding the physics of core dynamics and magnetic field generation. Scientists build computer simulations of the geodynamo, models that solve the equations governing fluid flow and magnetic field generation in Earth's core. These simulations start with current magnetic field measurements, estimate the core flow patterns that could have produced those measurements, then evolve those flow patterns forward in time according to the laws of fluid dynamics and magnetism. These simulations are pushing the boundaries of computational physics. The equations involved are nonlinear and coupled. Changes in the magnetic field affect the flows, changes in the flows affect the magnetic field, and everything influences everything else. Solving these equations accurately requires dividing the core into millions of computational cells and tracking the evolution of flow and field in each cell. Even on the fastest supercomputers, simulating just 1,000 years of core evolution can take months of computational time, and the simulations are sensitive to initial conditions and uncertain parameters. Small changes in assumptions about core properties or current core state can lead to significantly different predictions for future field evolution. Despite these challenges, geodynamo simulations have become increasingly sophisticated and reliable. Modern simulations can reproduce many observed features of Earth's magnetic field, including the dipole structure, the westward drift of certain field features, and the existence of magnetic field anomalies like the South Atlantic feature. When researchers run ensembles of simulations, multiple simulations with slightly different starting conditions, they can estimate how likely different future scenarios are. These ensemble predictions don't give a single definitive answer about whether the South Atlantic anomaly will continue splitting or how fast it will grow, but they do provide probability ranges and identify which factors most strongly influence the anomaly's evolution. Space agencies recognize that continued magnetic field monitoring is essential not just for science, but for practical space operations. NASA operates multiple missions that provide magnetic field data, including the ICON satellite studying the ionosphere and magnetosphere interaction. The European Space Agency is already planning follow-on missions to continue Swarm's work when those satellites eventually fail. China and other spacefaring nations are launching their own magnetic field monitoring satellites. The trend is toward continuous monitoring from multiple platforms, ensuring there are no gaps in coverage even as individual missions end. This monitoring matters because the South Atlantic anomaly is not the only magnetic field feature that affects space infrastructure. The entire radiation belt structure depends on magnetic field geometry. Changes anywhere in the field can affect where radiation belts form, how intense they are, how far they extend. The auroral zones, regions near the magnetic poles where aurora occur and where charged particle precipitation into the atmosphere is strongest, shift position as the magnetic poles drift. Communication systems that depend on ionospheric reflection can be disrupted by magnetic field changes that alter ionospheric structure. We've built a technological civilization that extends into space, and that civilization needs accurate, timely information about the magnetic environment to operate safely and effectively. What's remarkable is how much we've learned in just a few decades of satellite monitoring. 50 years ago, the South Atlantic anomaly was barely understood beyond satellites' malfunction more often there. Today, we have detailed maps of the anomaly's structure, measurements of its evolution over time, models connecting it to core dynamics, and predictions about how it might continue changing. That progress reflects not just better instruments, but better understanding, a deepening grasp of how Earth's interior, its magnetic field, and the space environment all connect into a single interactive system. But understanding is only the first step. The real question, the one that ultimately matters most for humanity's future, is what we do with that understanding. How do we adapt to a changing magnetic environment? How do we protect the space infrastructure we depend on? And perhaps most philosophically, how do we think about living on a dynamic planet that's constantly changing beneath our feet and above our heads? That perspective, that relationship between human civilization and the planet we inhabit, is where this story ultimately leads. Step back for a moment and consider the scale of what we've been discussing. Nearly 2,000 miles beneath your feet, liquid iron flows in patterns controlled by temperature differences, rotation, and structures we can only detect indirectly through seismic waves. Those flows generate a magnetic field that extends tens of thousands of miles into space, creating an invisible shield that has protected Earth for billions of years. That shield has a wound over the South Atlantic Ocean, a vast region where protection weakens because of how flow patterns in the core interact with dense structures in the deep mantle. And that wound is changing, splitting into two lobes, evolving on timescales of years and decades in response to core dynamics that take place over centuries and millennia. Everything about this is dynamic. Nothing is fixed. Earth isn't a static ball of rock with unchanging properties. It's an active, living system, not living in the biological sense, but alive with motion, change, evolution, occurring across every scale from the core to the magnetosphere. The magnetic field we depend on has reversed hundreds of times over Earth's history. The continents have rearranged themselves. The climate has swung between ice ages and warm periods. Everything about our planet is temporary when viewed over geological timescales. We just happen to live in a narrow window of time when certain features, the current magnetic field configuration, the current climate state, the current arrangement of continents, feel permanent because they change slowly relative to human lifespans. The South Atlantic anomaly reminds us that slowly is relative. For a geologist studying rocks that are millions of years old, the anomaly's evolution is breathtakingly fast, a magnetic field feature reorganizing itself in decades rather than millennia. For a satellite engineer planning a mission that needs to operate for 10 years, the changes are concerning because they might significantly affect the radiation environment the satellite will face during its operational life. For you, watching this unfold in real time, it's a rare opportunity to see planetary processes in action during your lifetime, rather than having to reconstruct them from ancient rocks. What does this mean for how we should think about the future? First, it means accepting that the space environment isn't a fixed background we can design for once and ignore. It's dynamic, it changes, and our space infrastructure needs to be designed with that dynamism in mind. Satellites should have enough radiation shielding to handle not just the current South Atlantic anomaly, but reasonable growth and intensification over their operational lifetimes. Mission planners should build in flexibility to adjust operational procedures as the radiation environment evolves. Insurance and financial models for space infrastructure should account for the possibility that the environment gets worse before it gets better. Second, it means continued investment in monitoring is essential. We can't adapt to changes we don't measure. The Swarm mission has been invaluable, but it's one mission with a limited lifetime. Ensuring continuous magnetic field monitoring requires commitment to funding and launching follow-on missions. It requires maintaining ground-based observatories even when budgets are tight. It requires international cooperation because magnetic field monitoring needs global coverage, not just measurements from one country's satellites. This isn't glamorous work. It doesn't produce stunning images like space telescopes or exciting discoveries like planetary missions, but it's fundamental infrastructure for understanding our planet and protecting our civilization's extension into space. Third, it means recognizing that we're learning to live sustainably in space, the same way previous generations learned to live sustainably on Earth's surface. Early civilizations had to learn that rivers flood, that droughts happen, that climate varies, and that building permanent settlements requires adapting to those environmental realities. We're going through an analogous process for space. We're learning that the space environment isn't a perfect vacuum with no hazards. It's filled with radiation, charged particles, magnetic fields, and dynamic conditions that affect our technology. Learning to operate reliably in that environment long term requires understanding what normal conditions are, what extremes can occur, and how to design for both. Here's what empowers me about this story. We're not helpless. We're not victims of cosmic forces beyond our control. We have the ability to measure, to understand, to predict, and to adapt. The South Atlantic anomaly isn't an unsolvable problem. It's a known challenge with engineering solutions. We can build better radiation shielding. We can design more radiation-tolerant electronics. We can place satellites in orbits that minimize anomaly exposure when practical. We can develop operational procedures that protect critical systems during high radiation passes. None of these solutions is beyond our current technological capabilities. They just require resources, planning, and commitment to implementing what we know. And what we know is growing. Every year, scientists publish new research refining our understanding of core dynamics, magnetic field generation, and the connections between deep Earth processes and surface effects. Computer simulations become more sophisticated, running on faster machines with better physics. Measurement techniques improve, allowing more precise tracking of subtle magnetic field variations. We're building toward a future where we can predict magnetic field evolution years or decades in advance with real confidence. Not perfectly, because complex dynamic systems always have uncertainty, but well enough to plan effectively. If you want to stay connected to this evolving story, there are resources available. The European Space Agency maintains public websites with swarm mission updates and magnetic field data visualizations. NASA provides similar resources for its Magnetosphere missions. The World Data Center for Geomagnetism archives magnetic field measurements from observatories worldwide, making them available to anyone interested in tracking long-term trends. These aren't locked behind paywalls or limited to professional scientists. The data is open, the story is ongoing, and you can follow along as scientists continue unraveling how Earth's magnetic shield behaves and changes. What I want you to take away from everything we've explored together isn't fear or anxiety, it's awareness. Awareness that Earth is more complex and dynamic than most people realize. Awareness that invisible systems you've never thought about, like the magnetosphere, profoundly affect the technological civilization we've built. Awareness that change is normal, not inherently dangerous, and that understanding change gives us power to adapt rather than simply endure. The South Atlantic anomaly is growing and splitting. Yes, it's affecting satellites and might affect space operations more significantly in coming years, but it's a manageable challenge for a civilization capable of putting sophisticated instruments in orbit, modelling planetary core dynamics, and engineering solutions to radiation exposure problems. We live under a changing shield. That shield has protected life on Earth for billions of years through countless magnetic field variations, reversals, and evolutions. It's protecting us now, even with a weak spot over the South Atlantic. and it will continue protecting us as scientists monitor its behaviour, engineers adapt our technology, and we collectively learn to operate sustainably in the space environment our magnetic field creates. That's not a story of vulnerability, it's a story of capability, understanding, and adaptation. The South Atlantic anomaly matters because it's real, because it's changing, and because we depend on technology that operates in the environment it affects. But it matters even more because it represents our growing ability to understand Earth as a complete system, core to magnetosphere, deep interior to space environment, slow geological processes to rapid technological adaptation. We're learning to see our planet whole, to track its changes, to predict its evolution. That understanding makes us better stewards of both Earth itself and the space environment surrounding it. If this story resonated with you, if understanding the invisible shield above us and the dynamic core beneath us changed how you think about the planet we inhabit, then share that understanding, talk about it, ask questions, stay curious, hit that like button if this added value to your perspective, subscribe to follow more stories about the dynamic processes shaping our world and our place in the universe. And drop a comment, seriously, tell me where you're watching from, because every single one of us lives under this same magnetic shield, and understanding our shared connection to Earth's invisible protection changes how we see ourselves as a global civilization. Earth is dynamic. The magnetic field is dynamic. The space environment is dynamic. And we, equipped with understanding, technology and adaptability, are learning to thrive in that dynamic reality. That's the real story of the South Atlantic anomaly. Not a tale of crisis, but a chapter in the ongoing story of humanity, learning to understand and work with the magnificent, complex, ever-changing planet we call